So now when we do have a better handle of what's happening on a Snoopy bus, we can discuss the current synchronizations that we have designed, as well as designing even better synchronizations for scalability. So this is a picture of the code that we've discussed before about an optimistic test and set lock spin optimization. So once more, the idea is that when you would like to acquire a lock, you perform the lock operation, you get into this infinite loop, and you try once to see if this atomic operation for test and set will succeed to get you the lock. In other words, if the memory location where the lock variable is, if an atomic test and set to that memory operation will return you the 0 while you atomically set some other value to that location. If so, you break out of this infinite loop, else you go into this fairly mundane while loop where you just do read operations, just read for as long as the value is not 0, and once it becomes 0 again, you get excited, you fall out of the while loop, and you once more try the test and set operation. We have before discussed the kind of coherence overhead that's associated with this operation, but now when we better understand how buses are implemented, we can go down to the detail level and discuss the overhead of this still fairly efficient way of doing locks. So here it is. While one of the threads in our system is in the critical section, all the other threads will be happily spinning on local variables in their caches, creating no transactions on the bus, and all of them will be spinning. Once our hero, the thread, gets out of the critical section, it will signal this by writing a big fat value 0 to the lock variable. Writing that 0 means it has to send one invalidation transaction across the bus. While doing so, it will invalidate all the cached copies of the lock variable. Still, all those threads will stay in the while loop, only that their value have now been invalidated. Next thing that happens is that while they're still spinning in their loops, trying to fulfill the while property to see if they're going to be there, they have to perform read to share operations. So all the threads, apart from the one that was in the critical section, will now perform read to share transactions on the coherent bus. So n-1 RTSs will appear on the one in order to allow for all of them to test to see if L is equal to 0. They will all see that L now is equal to 0. They will all fall out of their while loop, the mundane while loop where they spin on local variables. They will all get really excited and try to go for the lock. We have a round robin fashion. So most likely, so this is the one that was in the critical section, and we have a round robin fashion. So most likely the one that's next to it in order will be the one that will perform its test and set operation first. So we'll see the first test and set operation will create one invalidation message on the snooping bus. It will get into the critical section. So it will start to do good work in the critical section. While it is in the critical section, all the other of its friends have also got excited to see that the lock variable got the value 0. So they will also try their best to get the lock. So they will all perform the test and set. So there will be n-2 test and sets that will create n-2 read to write operations on this bus. So they will all create n-2 read to write operations on the bus, which will means that they will invalidate each other. while they do so. So after they've done their test and set, they will get invalidated. So there will be another n-2 read to share operations for them once they got the bad news from the test and set, and they will try to get in to the while loop again. So the first problem here is there is lots of Snoop activity that will slow down the handover of the lock, which is the time it takes until between the previous thread in the critical section performs the unlock, decides to perform the unlock until the next thread to get into the critical section is there. And that's really bad news. So the question is, how many batch transactions will there be between that the previous thread that was in the critical section decides that it wants to get out until the new thread is in the critical section? And the number of transactions that I'm requesting here is including the transaction it requires to perform the lock as well as the unlock. So I tried my best to calculate the exact number here, but what I really am asking you is, does it take, in proportional to 1 or 2 transactions? Is it proportional to 2 n transactions or just 1 n transactions? Try to do the exact calculation and see which solution comes closest to your guess. So fortunately, it's actually the last one. It's the invalidation that will release the lock. It's the n-1 transaction that will give the spinning threads hope. They will all see that the lock changed the value to 0. And it will be the transaction that the first to perform the test and set, this transaction, will perform before it gets into the critical section. After that, there will still be lots of activity. So the next problem is that the new winner will get into the critical section, but it will still be slowed down by more traffic even after that has happened, even before it gets into the critical section. So my follow-up question is, what's the total number of bus transactions that are queued up in the system between the previous thread is done with its critical section and wants to get out, and until all the activity that happens after that? And here, once more, I've tried to calculate the exact number, but my question to you is really, is it in the order of 1, 2, 3, or not the order of, but is it proportional to 3n? Is it proportional to 2n? Or is it just proportional to n? So unfortunately, it is proportional to 3n. So first we have the invalidation of the release. We have the invalidation of the new to acquire. We have, so that's the 2 invalidations. We have n-1 RTSs for all the spinning threads to just get the hoop up. And then we have n-2 read to write for them to fight over the lock using their test and set. And then finally we have n-2 RTSs for them to get back into their cozy state of spinning in their own local caches. Obviously, these many transactions, both for the handover as well as all the total amount of transactions created, could create problem if the number of n is large. So we're going to look in the future into how we can improve that. Right now going to look at one simple solution how we can improve that with what's called a queue-based lock. So this is the most simple example I know of a queue-based lock. It's called a ticket-based queue-based lock. So here, the lock itself contains the the structure that represents the locks contains two different values or variables. One is a ticket and the other one is now serving. In order to understand how this lock works, the best thing is just to walk into the grocery store and go back and try to get to the cheese counter. So normally in the cheese counter there is a machine where you can pull out a ticket, pull up a number from that ticket, so you can get in line behind all the other customers who are waiting for at the cheese counter. And above the cheese counter there is a big sign saying now serving, and it's one specific number. So what you do here when you get into the lock is you have a local variable, which is my number, and that my number is assigned to the value you get if you increment the ticket number, the one you get out of the machine. Okay, and once you got your number, you get into an infinite while loop, and as long as my number is not equal to now serving, you just wait there, just like you would do in the cheese counter. Then you may ask yourself, how do you implement this kind of increment a variable? Eric, you told me earlier you need some kind of lock structure to do that. Well, you do that if you want to implement a simple version of increment, but there is actually a more efficient way of doing that. If you remember, we had a transaction which was called compare and swap. We're going to use this now to implement a lockup-free increment. Okay, so you have some label start, and at start you say that register 1 is equal to whatever memory location you would like to increment, and then you say register 2 is equal to R1 plus 1. Okay, then you do the compare and swap, and if you remember, compare and swap said if one register is equal to the memory location, then you swap R2 with that memory location. Well, we have all the suspects we need to perform that the task now. So if R1 is equal to memory location, that means that since we read the memory location into R1, it hasn't changed. That's what that says. If that is true, then we swap R2, which is R1 plus 1, with the memory location. If that is not the case, I write in this pseudocode, we go back to start again, and we keep repeating this over. So we sort of with three fairly simple instructions that we have readily available in CPUs, we can perform an atomic increment without actually introducing extra locks and so on. So this could easily be done. So now we can sort of implement the ticket machine that says that everybody comes there and pulls out the number will get incremented by 1. And then we have, while my number is not the now serving number, you just wait. Unlocking, once you are in, once you've seen that your number is equal to now serving, you buy your cheese, and now when you're done buying cheese, you unlock, and the way you unlock is you increment now serving, and you don't need any atomic operation to do that because you're the only one that can increment now serving. So this is what's called a queue-based lock. It's a first come, first serve, just like the cheese counter. This is unlike the spin locks, the test and set locks we discussed before. This is strictly in order who comes there and pull their tickets. So that sounds like it's a good thing, because it sounds like it's a much more fair lock. We'll have a separate discussion about that in a little while. The question is, is this any better or worse than the locks we've used before? So I claim there's less traffic at handover for this lock than it is for the test and set. But I leave it to you to judge how much less traffic there is. So how many transactions will be between the exit of a previous thread leaving the critical section until a new thread is in the critical section, and once more including lockers and unlocks. I've also tried now again to count the number of, count the number of transactions. And the first alternative says it's 1 invalidate, and it's either number between 1 and n-2 reader shares. The second one is simply 1 invalidate. And the third alternative is 1 invalidate and then n-1 reader shares plus 1 invalidate, similar to what we saw for the test and set. So the correct answer is the first answer. So 1 invalidate, that is what's required when you update now serving, because everybody is looking at now serving. Everybody's spinning on now serving, so you do 1 update, 1 invalidate there. And then it requires for everybody, standing there looking at the ticket in the spin loop, it depends on how long time it takes until the one with the magic ticket that will win gets there. It could be anything between 1, which is the best case, which that means that it would be the very next one in the round robin fashion, or worst case would be n-2, that will be the last one in the round robin fashion, that is the next one to be served. So it's not just the first one to perform this task. Okay, it's a specific thread which is have been chosen to be the next one to enter the critical section. We have to wait until it enters the critical section. So all in all, how many bus transactions will we need to queue up before we manage to change owner? So not just before we get the next one gets into the critical section. Will it be the order of 3n, order of 1n, or order of 2n? So unfortunately, it is fortunately, it's the second one. So we need 1 invalidate, which will invalidate everybody else. And then we need, for all the happy people who are spinning here, waiting for the good news, they are all just doing reader shares. And that's how many transactions will be generated. So compared with the test and set we saw before, where we had an order proportional to 3n, now it's just proportional to 1n. So it's a factor 3 improvement using this lock. So clearly we can design locks that are more efficient, even more efficient than the optimistic and or pessimistic test and set. In the next movie, we're going to look at even more efficient locks when you get up to hundreds and thousands of threads. Before we do that, let's look at the performance of these kind of locks.